Okay, so good morning, everyone. It's a pleasure to have Odilon Lourenço today here with us. So Odilon completed his studies at the Federal University of Federal Fluminense, UF. And now he's a professor at ITA. And he's a theoretical nuclear physicist. And he works with different models of hadrons and quarks. And today he will be talking about how to incorporate the effect of incorporating dark matter in particular models of hadrons and quarks. So Odilon, take it away.
Thank you. First of all, I would like to thank the kind invitation to be here. Thank you, Marcia, Dimitri, and Farinaldo. It's a pleasure to me to come back here. I have been here in 2022 for a conference. And now I'm talking about hadronic and quark and effective quark models in the description of compact stars with some dark matter contents, okay? First of all, I'll give some basic concepts about nuclear and hadronic physics for those that are not used to this kind of theory. I will present some phenomenological models that are the models that I'm working. Then I will present some evidence for nuclear matter and how to couple it to these models, okay? There are two ways, at least, to do it. One of them is from the one-fluid approach, and another one is from the two-fluid formalism, okay? So in this, I will concentrate in this case with a particular hadronic model that I think it's very interesting because there is some interesting correlations there. Then some dark matter models that are used to describe this kind of system, and then a particular effective quark model, and both of them coupled with dark matter and some main conclusions, okay? So, okay, this is the typical size and energy scale picture, okay? So if you are interested in study atoms, so you have to recognize that in meters, they have the size of 10 to the minus 10 meters, okay? So if you go deep inside the atoms, you'll find the nucleus that has this typical size, 10 to the minus 14. Then if you go even deeper, you see the proton that has this size, 10 to the minus 15, and so on, okay? So in the energy scale, you have electron volts for the energy scale for an atomic nuclei. The nucleus themselves has an energy of mega electron volts, okay, MeV, like the lead nuclei, for instance. And a proton, if you want to study the composition of the proton, you have to go to increase the energy scale, okay, to giga electron volts. Okay, so of course, as if you decrease the size, you increase the energy. Okay. So if you want to study hadronic or nuclear physics, so you are interested in hadrons. Okay, what are hadrons? Hadrons are the set of two objects, baryons, that are objects that are composed by three quarks. Protons and neutrons are typical examples of this kind of objects, okay? So you can refer to protons and neutrons as nucleons, as a generic name, okay? With regard to the statistical, they are fermions because they have a half integer spin, okay? And they interact each other through a meson exchange mechanism, okay? And mesons are composed by one quark and one antiquark, like pions, okay? And all of them are bosons because they have integer spin, okay? So the set of particles here, or objects to be more specific, they feel the strong interaction, okay? So we call all of them as hadrons, okay? So what are the aims of hadronic or nuclear physics, okay? It's to study the laws that govern atomic nuclei, understand the nuclear interaction, investigate general nuclear properties, such as the ones that you can extract from nuclear reactions and other related phenomena, okay? So, in order to perform this analysis, you have basically two tools. One tool from the theoretical point of view, that is quantum mechanics, and from the experimental point of view, we have to use accelerators in order to study nuclear or hadronic physics, okay? So, so in order to understand from the theoretical point of view, that is the focus of this presentation, okay? You have to understand some basics from the nuclear potential, for instance, okay? So the nuclear potential, different from other interactions in nature, it is not completely known, okay? Like the electromagnetic force or the gravitational force, for instance, okay? So because of that, we need models. We need to model the nuclear potential. But we know very clearly some basic features of this kind of potential, okay? So if you have the distance between two nucleons, two protons, for instance, if this distance that I'm calling here R, if it approaches to 0, then you know that the interaction between these two particles must be strongly repulsive. Otherwise, the nucleus would collapse. But we know that nuclei exist. So this is a basic feature that needs to be satisfied for a realistic nuclear potential, okay? So inside the nucleus, the strong interaction needs to be attractive, okay? Otherwise, nuclei wouldn't exist as well. And it should be stronger than the Coulomb repulsion, okay? In order to make a nucleus stable. And outside the nucleus, this interaction must be negligible. Otherwise, all universe would collapse, okay, due to the nuclear force. Okay, so if you can draw here, this is a typical form for the nuclear potential, okay? It's a very repulsive here in the small distance and attractive inside the nucleus and goes to 0 in distance greater than typical nucleus size, okay? So a direct consequence of this kind of potential is the saturation of the density. That means that if you add in a nucleus more nucleons, more protons, for instance, or neutrons, the nuclear force will be, the particles inside the nucleus will interact with the surrounding nucleons. But if you continue adding particles in this nucleus, the nuclear force is not able to act in the outer nucleons, so the density, the consequence is that the density will be constant at some point, okay? So this is a typical saturation density for the lead nucleus, okay? 208 lead. That is about 0.15 fermi to the -3. That in gram per cubic centimeter is given by this huge number here, okay? The density of water in this unit is equal to 1, okay? So you can compare how dense is this kind of system, okay? Okay, the binding energy is another very interesting concept that is present in the analysis of all these kind of phenomenological models. What is this quantity exactly? Is actually the difference between the energy of a system composed by z protons and neutrons separately and free system in comparison to the nucleus formed by the same particles, okay? So how it is possible to convert mass and energy because of the famous formulation, the Einstein formulation relating energy and mass, okay? In nuclear physics units, we take C equal to 1, then we can use the same unit for energy and mass. So this difference between these two systems in mass is called binding energy, okay? So it is parameterized, for instance, by this famous formula that consider macroscopic properties of the nucleus, okay? Like the volume, the asymmetry between protons and neutrons, the kind of surface that nucleus presents, the Coulomb part of the interaction, and so on, okay? So this is a macroscopic way to treat properties of nucleus, of nuclei, okay? So for a symmetric nuclear matter system that is characterized by Z equal to N, the same number of protons and neutrons, and by the volume very large, this binding energy is given by this number, okay? Around 16 MeV. And to construct a many nucleon system, you can do it by some ways. One of them is via through a microscopic analysis, like this one here. And we have also another option that is to treat microscopic models or ab initio models, in which we have to correctly propose a nucleon-nucleon interaction as a starting point. But this formulation will present some free parameters to be determined, so you can use no data from few nucleon systems like the deuteron, that is a bound system composed by one proton and one neutron. So you know very well this kind of systems, like scattering data, for instance, okay? So the parameters of the nucleon-nucleon interaction will be adjusted by reproducing this kind of system. So since we have this nucleon-nucleon interaction well determined, we can go for construct many nucleon system, okay? This is one way to do it. Another way is from phenomenological models based on the mean field approach or mean field approximation that consider a nuclear potential as one nucleon in particular feels the effect of the other one's nucleons by a kind of mean field potential, okay? So again, we have some free parameters to be determined in this kind of approach as well, okay? So you can determine these free parameters by looking at nuclear matter properties or finite nuclear quantities, okay? I'm interested in this kind of formulation, okay? I work basically with this one here. So there is some models that are based on this second approach here. For instance, we have non-relativistic models like the SCRIM one that propose mean field potential with this form. We have basically a delta function here. That means that two nucleons interact each other when they are very close each other, okay? So from this kind of potential, you can construct the energy per particle, for instance. In this case, this expression is given for symmetric nuclear matter when we have the same number of protons and neutrons, okay? So, but this is an expression for an infinite system, okay? A gas of protons and neutrons in particular, okay? Good, so this is another non-relativistic model Okay, this is the nuclear potential for this model, the Gogni model, that now considers finite range effects. Okay, you can also extract the energy, some thermodynamical quantities like the energy per particle, in this case for asymmetric systems, okay, asymmetric nuclear matter, and so on. We can also propose some relativistic versions of these phenomenological models, like this one. We call it here relativistic mean field models, okay, that in which the starting point is the proposition of a Lagrangian density that can be used to extract energy density, for instance, okay? This is the case for this generic model, the energy density for asymmetric nuclear matter in this case, okay? So I will use this particular model to describe compact stars with dark matter, okay, later on. I will focus in this kind of relativistic models, okay? So, okay, if you extract or if you determine the energy density for a typical model, non-relativistic or relativistic one, we can also construct the pressure, or if you extract the pressure and the energy density, you are able to determine all the other relevant thermodynamic quantities for that model in particular. Okay, so like this one, the incompressibility, the Skinner coefficient. The incompressibility is defined, for instance, as the how the system responds to variations in pressure. So it means that how the system can support compression. Okay, this is a very important quantity. We have here, for instance, the symmetry energy of the system that is defined as a derivative of the energy per particle, but in more physical terms, it means it is defined as the energy cost that you have in order to convert symmetric matter and pure neutron matter. Okay, and we have the slope of the symmetry energy, the curvature, and the skewness of the symmetry energy, and so on. Okay, but in order to, these are the famous nuclear matter bulk parameters that are defined, all of them in symmetric system and at the saturation density. Okay, so each model of them that I presented before, for instance, Sturm model, Gogni models, or the relativistic mean field model, has a particular, each free parameter that are each free parameters of each model, each set of free parameters of each model defines a particular parametrization, and each parametrization has a particular set of nuclear matter bulk parameters, okay? If you consider only Sturm and relativistic mean field models, we have more than, let's say, 500 parametrizations, okay? Only if you consider two of these three phenomenological models, okay? Okay, so, okay, all of that, all of these kind of calculations are presented at 0 temperature, but you can also investigate finite temperature properties of this kind of hadronic models. For instance, you can investigate how the pressure evolves as a function of the density, for instance, okay? And you see here that we have a direct consequence of the nuclear potential, okay? So in very low densities, you have ideal gas behavior, because at very low densities, we are, if you consider the distance between two protons, for instance, we are here in this region in which the potential is vanishing. So you have a ideal gas behavior, okay? So as the density increases, the distance decreases. So you have we are in the attractive part of the nuclear potential, so the pressure starts to decrease. Then, as the density continue increasing, you attain the region in which the nuclear potential is attractive, is repulsive, sorry. In this kind of region, in this particular region, you have again the pressure increasing. So in this case, you have a typical van der Waals behavior of this kind of hadronic models. Okay, so you have all the phenomena that are related for the van der Waals gases. For instance, a liquid-gas phase transition that are presented by the hadronic models as well. Okay, but I'm not show anything about finite temperature. So I'm restricted to 0 temperature. Okay, so I'm going to use this kind of phenomenological models, in particular this one, in order to describe compact stars with dark matter. Okay, so why investigate dark matter? Because we have very clear evidence of this kind of non-luminous matter. Okay, for instance, the rotational curves of spiral galaxies. Okay, this is a typical one. The rotational velocity of one star of a certain galaxy as a function of the distance between this galaxy, this star, and the center of the galaxy. By the Kepler's law, we would have this behavior, okay? But what we observe is that this behavior is almost flat here, okay? So in order to reproduce this kind of observational behavior, we would need that the mass of the galaxy would vary with the distance, okay? So this is the general picture. So we would have a galaxy surrounded by an envelope of dark matter, of this non-luminous matter that was called dark matter, okay? Suggested first in 1937 by Zwick, okay? So if you have this kind of matter in the universe, why not they are present in the interior of compact stars. Okay, so let's check it. Okay, so as I told before, there are at least two ways of coupling dark matter with this kind of phenomenological models. One of them is from the one fluid approach, in which you have only one model with both sectors interacting each other. Okay. For instance, by the Higgs exchange mechanism. Okay, so this is the typical Lagrangian for this kind of approach. We have this chi here is the Dirac field representing the dark particle, the dark fermion, to be specific. Okay, this is the mass of the dark fermion. We have an interaction between the Higgs boson and the dark fermion. This is the kinetic parts of the Higgs boson. And we have an interaction between the Higgs boson and the visible sector, okay, the ordinary sector. This psi here represents a nucleon, okay, for instance. Plus a typical Lagrangian density for the phenomenological hadronic model, okay? So this formalism has been used a lot recently. Okay, these are some examples in of papers that do it. We can use the mean field approximation to describe the field equations and the equations of states of the model. So, okay. So for this particular Lagrangian, as I said before, I'm going to use this phenomenological relativistic mean field model, okay? So these red quantities are the coupling constants of the model, the free parameters that we determine by imposing some values for that book parameters that I presented before, okay? We will also apply the mean field approximation to this, for all these fields here, and for the Higgs field as well, okay? For the entire Lagrangian density. By doing that, we find the field equations here, okay? So here are the field equations for the sigma, omega, and rho meson, okay? These mesons here, this meson sigma is responsible for the attractive part of the nuclear interaction. The meson omega takes into account the repulsive part, and this rho meson describes the asymmetry between protons and neutrons, okay? And then we have also self-interactions between the mesons, okay? And we can extract from this Lagrangian density and the mean field approach the equations of the field equations for the mesons field, the field equation for the Dirac nucleon field, as well as for the Dirac dark field. Okay, so we see that we have a kind of back reaction, because you see here the Higgs boson affects the effective mass of the nucleon, as well as the effective mass of the dark particle. Okay. From the Lagrangian density, we can extract the energy momentum tensor, and from this quantity, you can extract energy density and pressure. Okay. These are the main equations of state that are needed to describe the whole system. Okay, so these are the forms for these quantities. Okay, so as we are in a relativistic approach, we have here the relativistic energy and pressure, of course. Okay. Okay, so but we can also go further in investigating the role of the Higgs boson in this kind of approach. Actually, the Higgs boson plays no role here, okay? We can check it by analyzing these two expressions, three expressions actually, okay? The first two ones are related to the effective mass of the nucleon and the dark particle, okay? If you see, this last term here is the one that is due to the Higgs field. So if you plot this quantity as a function of the density, you see that this number is very, very small. This is dimensionless quantity, okay? So it's very, very small. So you can safely disregard this quantity. So in for practical purposes, the nucleon field, the nucleon mass is not affected by the Higgs field. Okay, so the same you can check for the dark particle mass. Okay, the effective dark particle mass. So if you analyze this quantity as a function of the density, you see that this quantity is very, very small. So for practical purposes, we can safely take the effective dark particle mass as constant, okay? So, but you can ask, what about the energy density? Because in the energy density, you have the Higgs contribution as well, okay? But you can compare this Higgs distribution with this sigma meson, this Higgs term, with this sigma meson term here, okay? If you plot this term here as a function of the density and compare with this one, we see that this guy here is very, very small in comparison to this one. So you can safely disregard this guy here. So for practical purpose, including dark matter, a fermionic dark matter, or coupling a fermionic dark matter with this kind of phenomenological models is only to consider the kinetic part of the dark particle, okay? There is no contribution coming from the Higgs field. Okay, so, but why to construct energy density and pressure? Because these quantities are needed as input to describe a compact star, okay? I'm interested in, so this is a general picture from the evolution of stars. So a star, the starting point for a compact star is a stellar cloud with proton stars. Depending of the mass of the stars, it can evolute with this part here to ending in a white dwarf, or by this other path here, by ending in a neutron star or a black hole, depending on the mass of the star, okay? I'm interested in this kind of star here, okay? Neutron stars. So, in order to describe a neutron star, we need to solve the Thomson-Oppenheimer-Volkov equations, okay, that are defined here. And the input for this kind of equations are exactly the energy density and the pressure. So because of that, I'm focused on these quantities in the previous slides, okay? So you need to give as input this particular, these two particular thermodynamic quantities, okay? So if you do that, and if you consider a particular value for the Fermi momentum of the dark particle, you can construct the mass radius relationships like these ones that I'm presenting here, okay? This is for the NL3 parametrization of the hadronic sector, okay? So no dark matter is represented by this black curve, and if you include dark matter by increasing the dark Fermi momentum of this dark fermion, you see that the maximum mass decreases, okay? This is verified by this particular parametrization of the hadronic sector, as I said before, but for other ones as well, okay? So this is EIOPB is another hadronic parameterization, and DM0 means Kf equal to 0 GeV, DM3 Kf equals 0.03 GeV, and so on, okay? So you observe the decreasing of the maximum mass of a star by increasing the Fermi momentum, okay? This is not good because the latest observational data says that the stellar masses needs to be greater than 2 solar masses, at least, okay? So if you have a model that decreases this mass, it's not, in principle, compatible with observational data, okay? Not in this case, because in this case you see that the decreasing is not too strong enough to decrease the maximum mass below 2 solar masses, but in general, this is a not good behavior, okay? Okay, but this approach takes into account only one let's say only one Lagrangian density. So, okay, so there is only one fluid interacting each other through the Higgs boson, but there are another approach that consider two separated fluids, okay? In this case, they do not interact anymore, each other, but they only interact through gravitational interaction, okay? So in this case, we have a generalized TOV equations. So in this case, we have 4 instead of 2 TOV equations, and we have energy density and pressure for the visible sector, okay, and for the dark matter sector, okay. So we now have to consider 4 differential equations to solve in this kind of formalism, okay. So we are working at the moment in solving these equations for a particular hadronic model that I will present briefly here. And we are interested in see the effects of this particular hadronic model in the whole description, okay? So this particular hadronic model has the inclusion of this kind of short-range correlations, okay? What are these correlations exactly, okay? So we know that in experiment like that, for instance, we have here a very energetic incident particle, an electron, for instance, okay? If it hits this heavy nucleus, we see that it can remove one nucleon, one specific nucleon, but actually, in 20% of the time, this nucleon, this proton, for instance, is not isolated. We verified a correlated partner for this nucleon, okay, in the 20% of the time. And in the most of the time, in this kind of output, we have a pair of a neutron-proton pair, okay? So in the majority of the time, okay? So this is what we call short-range correlation. What this kind of correlations have as consequences for these phenomenological models. So you have this kind of consequence, okay? If you construct here the single nucleon momentum distribution as a function of the momentum, for a free Fermi gas, that is the way in which we construct the kinetic part of that phenomenological models. The free Fermi gas changed to this new distribution, okay? We observe a depletion for moments below the Fermi momentum, okay? And for momenta above this Fermi momentum, you see a tail, okay, with this form. Okay, so we have some quantities that I'm not going into the details, but for practical purpose, we need to modify all the integrals, all the momentum integrals of these phenomenological models to these new ones that includes this tail here. It's called hard momentum tail, okay? So this is the modification. So we are investigating what is the consequences of these modifications in the dark matter admixed neutron stars, okay? So first of all, we need to analyze what is the consequence in the equations of states of this kind of model. We can construct here energy density and pressure. Here, energy density and pressure of the hadronic side only for now, okay? So we have this kind of modification in the kinetic parts. So if you take the high density limit of these equations, we will verify this kind of effect, okay? So this non-leading term here that I'm calling beta prime is directly affected by the short-range correlation by these functions here, okay? These particular functions, okay? So these are the beta prime form, okay? So it directly takes into account the consequence of the short-range correlations, okay? So if we do a plot of this beta prime as a function of the neutron, the proton fraction, for instance, we can see that by varying the nuclear matter bulk parameters, we can see that the beta prime here, the full curve is the beta coefficient with short-range correlations, and the beta notation here takes into account the same parameter without short-range correlation. You see that this guy here is only it's only small than the other ones. Okay, so for practical reasons, we see that the inclusion of short-range correlations leads to stiffer models. Okay, the pressure of this kind of models with short-range correlations included is greater than the corresponding ones without this phenomenology. Okay, this is the main message. Okay, so why this is important? This is important because if you have a more stiff equations of state, we can produce more massive neutron stars. Okay, this is the neutron stars without dark matter. Okay, just to see the effect of the hadronic side itself. So you see that if we included this kind of correlations, we produce more massive neutron stars, as the observational data indicates. Okay, but now we are interested in analyze the effect of dark matter coupled to this kind of models. Okay, so we can consider both two kind of dark matter models that are being used in the literature nowadays. One of them is fermionic, the dark matter model, okay, that produces these two equations of state, okay, a kinetic term plus a interaction term here, a repulsive term, okay, and we also have a bosonic version of this kind of dark matter models, okay, that can be used to extract the energy density and pressure as well. These are the equations of states, the pressure as a function of energy density of these both models, and we see that the fermionic models is more stiff than the bosonic one, like as we expected. Okay, and here we have the sound speed as a function of the energy density, just to check that both models are causal. They do not break causality. Okay. Okay, good. So if you if you solve the two-fluid formalism by consider, for instance, the fermionic dark matter model and a model with short-range correlation, we verify mass radius diagrams like this one. Okay, so the full curves denote the relativistic mean field model with short-range correlation, and the dashed curve without this kind of correlation. You see that the effect of increasing the dark matter content, here we have this percentage here, that is the percentage, the ratio between the mass in this star corresponding to the dark matter over the total mass. This kind of the increasing this number here produce the same effect, decreasing the maximum neutron star, okay? Neutron star mass. But if you include short-range correlations in the hadronic side, we see that this decreasing is balanced by the increasing caused by the short-range correlations, okay? So we are investigating this kind of effects, okay? Okay, so, but this is for hadronic models, okay? We can also use the two-fluid formalism to analyze quark stars coupled to dark matter, okay? How can we do that? So, just to give a motivation, this kind of compact stars are obtained at t equals 0, but at t equals 0 and very dense matter, like the matter that is presented in the compact stars, we are here in this region, okay? So in this region, we are in the non-perturbative region of the QCD, okay? So we have no way to use large QCD, for instance, so effective quark models are necessarily required in this region, okay, to analyze, for instance, quark stars. You can use a particular quark model, okay, for the visible sector of this coupling, like this one. So let me say in a few words which model is that. Okay, if you consider the Queensrÿ D Hamiltonian, you see that is composed by a kinetic part plus part in which we have the current quark masses plus an interaction part, okay, term. We can construct an equivalent model that encompasses this interaction part in the mass of the quark, okay? If you do that, and if you impose the same eigenenergy for any eigenstate psi, okay, if you do this imposition here, we can realize that this relationship holds, okay? This is a state that has a baryonic density different from 0, and this is the vacuum state, okay? So if you do that, you see that this constituent quark mass has this form here, okay? For a term that is due to the current quark mass plus an interaction term, okay? How we can find this interaction term? So I'm going a little bit fast in these details, but we can do it by using a particular potential that incorporates confinement and asymptotic freedom. So we can, using this guy here, we can extract the density dependent of this current quark mass, okay? So this is the model. So by finding this relationship here, we can construct the pressure and energy density again for this model that is basically the pressure and energy density of a free quark model, but with this density dependent taken into account, okay? So you do that, and if you apply the stellar matter conditions and so on, we need to find these two free parameters that are presented in this density dependent function here by satisfying the Bodman-Witten hypothesis, okay? So we can use, for instance, this pair of parameters, okay, to construct the quark stars, okay? So these quark stars, we can construct both for bosonic case and fermionic case. So here we are using dark matter that I presented before, coupled to quark matter, bosonic and fermionic cases for the dark matter, but coupling with quark matter, but only through gravitational interaction, okay? This is the two-fluid formalism. So you can construct mass diagram curves like that, and we see that they are very compatible with recent astrophysical data, okay? Okay, this is, we can also observe the profiles for a specific mass, for instance, for this mass with this kind of percentage for the dark matter. We see that the visible matter here dominates, okay, and so on. So, but this is, these are only details, okay? So, let me conclude. We are verifying that short-range correlations may lead to stiffer models, thereby producing more massive neutron stars. Neutron or quark stars admixed with dark matter content constitute a possible scenario consistent with astrophysical data, okay? And short-range correlations allow more dark matter content that are still compatible with observation. Thank you very much.
Thanks, Odilon. Questions?
So, thanks, Odilon, for your talk. So my first question is, so you described how the Higgs, the coupling with the Higgs, like coupling over the valve, right? In the very beginning.
Yes.
I think it was
the
like
first
18.
18?
Yeah. 18 or more. Yeah, so it's the same. I mean, you can go
I think
before, yeah, that one, yeah. That M star.
This one?
Yeah, so, okay, yeah. So you have F, M nucleus over the VAV, right?
Yeah.
So, so your conclusions are based on that the Higgs couples to dark matter suppressed by the VAV, right?
Yeah.
That's your conclusion. So, in the end, you concluded that the Higgs does not contribute much to the energy density, but it does contribute to the pressure.
No, actually the opposite. They do not contribute to the pressure, but they contribute only to the energy density, actually.
Yeah, okay, so could you go forward?
Yeah.
Show the one where you computed the plot with the pressure and that one.
This one. Yeah, only the kinetic term contributes, actually. This term drops and only this one survives.
Okay, I'm trying to understand. So, for instance, this energy density depends on the mass of the sigma squared, and also have the mass of the Higgs squared.
Yeah.
So what is embedded in this term to lead you to the conclusion that the Higgs does not contribute? Because from there, the Higgs mass is much greater than the sigma. So why the Higgs does not contribute much?
Because the Higgs field as itself, it's very, very small. 10 to the minus 15 something. That
what is small? The Higgs?
The Higgs field, I mean. In the field equations, if you compute all these field equations, this is the field equation for the Higgs.
Mm-hmm.
And if we perform, if you analyze the evolution of the Higgs fields as a function of the density, you see that it's very, very, very small. It compensates the higher value for the Higgs mass.
Okay, but then it has to do with the fact that the coupling is M nucleus over the VAV, right? Because let's say that this was order 1. Let's just assume that this is order 1. F over the VAV, M nucleus order 1.
Yeah,
not suppressed.
But let's see this guy here.
No, I'm just saying that yes, exactly. So let's say that this ratio is order 1. F over the VAV is order 1.
Yeah.
So would the conclusion still hold?
Yeah, because this term here does not contribute.
But it doesn't contribute because the VAV is large and F is what? Is small? F is the Yukawa-like coupling, right?
Yeah, these ones. We test for...
exactly. So let's say F is 0.2. The VAV of the Higgs is 245 GeV.
Yeah.
So this is very small. We are talking about something 10 to minus 3.
Yeah, but this is the expectation value of the Higgs field, no?
Right. So it's natural
to very
me
huge.
That once you add something that is order of 10 to minus 3, the effect will be small.
Yeah.
But if that coupling, I'm saying if F is proportional to the VAV, that coupling.
To the V?
Oh. Yes. So I'm just assume that this ratio is order 1.
Okay. We didn't test this kind of
I'm asking because there are models in which the coupling with the Higgs and the fermion is not suppressed by the VAV.
Okay.
Then it will lead to a conclusion where the Higgs might contribute to the
that's right. That's right. Yeah, that's right.
Okay.
That's right.
I'm just contemplating here.
Yeah. Okay.
Okay, so let me just take one more minute to ask one other question.
Okay, but Fernando, I think in this case, in the Lagrangian, this M nuclei over V is the mass of the fermion and not the dark matter itself. So in this case, you would have to change the Y that coupled in the Yukawa Lagrangian.
Yeah, I'm just contemplating whether if it's not so suppressed, let's say it's order 1, or maybe 0.1, I don't care.
I see.
The precise value, but I'm just saying that if this coupling is not suppressed by the VAV, then the Higgs might play a role.
But in this case, you have to change Y, not F.
You mean F?
Because F is the coupling with the fermion, which would be the quarks, I guess, in the star. Because this is the mass of the nucleus.
No. I won't change that one. That one is right. So the Higgs couples to dark matter proportional to the Yukawa. Now I'm thinking about the Higgs. How the Higgs couples to psi. It doesn't have to be suppressed by the VAV. Okay, anyway, we can discuss this later. So let's go to slide 37.
37, okay.
Yeah.
Yeah.
So you were saying at some point that you only considering gravitational interactions.
Yes, gravitational.
Which ones? Between the nucleons themselves?
Between the quarks. Here I'm showing quark stars. Between quarks and fermionic or bosonic dark matter.
So they only couple through gravity.
Yeah.
But then what is the role of the Lagrangian then? Because you have this dark vector and so on. So if they only interact by gravity, why you need the Lagrangian with a dark vector and so on? Because they reside before.
You mean, let me see.
Yeah, that one. So
This one, for instance?
Yeah,
Yes.
if it's just by gravity, so it doesn't matter the GV there. GV plays no role if it's just by gravity.
Actually, it does, because if we increase the repulsive interaction in one side, then we can, in principle, produce more massive neutron stars.
But V does not represent gravity, right?
No. V here is a vector field that represents only self-repulsive in the dark sector, only in the dark sector.
But so you're somehow mapping what gravity, the effect of gravity of the dark matter?
No. The effect of gravity comes from the only by the solution of the TOV equations. You see that there are some contribution in the, let's see, yes. Well, here we have the total pressure contributing to the visible part of the pressure and vice versa.
Yeah, okay, now go forward again.
Yeah.
Oh, up to the Lagrangian. Wait, it's not working?
Maybe here directly.
Yeah, okay, go back, yeah. So for instance, V is telling you how dark matter couples to each other, right? Through V.
Yeah. A repulsive term only.
Yeah, it will be just between themselves, self-interaction, as you're saying.
That's right.
But it's not gravitational.
No. This is only confined in the dark sector. The interaction in the dark sector.
Okay, but then when you say that you only consider gravitational, so it means that you're neglecting this interaction?
No. It means that I consider all the interactions in this sector, all the interactions in this one, and couple each other only through gravity. Different from the one fluid approach that we have only one fluid interaction with each other in both sectors. This is the general picture.
My question goes exactly in this direction. What happens, or if you already did it, or you know somebody who did it, if you consider that there is this new vector boson interacting with the fermions of the standard model, for example, with the quarks. So what's gonna happen? What you expected to happen in this plot that you showed?
If you have
if you have interactions between this new vector boson.
Okay, the Higgs, sector, for instance.
This vector is
this one. Okay.
Interacting with the quarks, for example.
Beyond gravity.
Yes.
Now
you have a very weak, I don't know.
In this case, I don't know, because in this case you are in between two formalisms. You are saying that if you consider both gravitational and the new interaction. Yeah. I don't know exactly.
That would be the case you were asking, like we were talking before. So you would have, for example, if we consider axion particle as a...
Yes. If you consider axion particles in this kind of formalism, I would say that I included here in a one fluid formalism.
Yeah, I think it's close enough. So, just to say, like the Higgs,
there
is nothing from the quantum field theory point of view
Mm-hmm.
prohibit the Higgs from coupling fermions, right?
Good. Because this is the coupling. Good.
And the Higgs also couples to dark matter.
Yeah.
As you included.
Yeah.
Therefore, dark matter does also couple to psi, to fermions as well. Because if they
Indirectly, né? Yeah.
so you construct a vertex, I find a diagram where the chi will couple to psi.
Directly.
Directly.
Okay.
S channel in this case. So you do have dark matter interaction with psi.
Good.
You do have this is unavoidable.
Yeah. Okay.
So that was beyond gravity,
Yeah, that's right.
and that's what he's asking.
Ah, okay.
What's the impact of having sizable? In this case, it's not. It's fine.
Yeah.
If you have sizable interactions between chi and psi, what happens
Yeah.
to the mass R ratio?
Yeah. That's a very good question. I don't know.
But in this case, the nature of the interaction will be different, right? Because now in this case you have
Yeah, but
proportional to the
we
mass.
also need to parameterize this vertex, no? The
Yes.
coupling constant. I don't know how we can determine this coupling constant.
You know how to do this. I mean, there are tons of models that you can throw using neutron stars.
I see.
Many of them.
many ways to search for it.
By including this new coupling between chi and psi.
Yeah. So in general, if you do take into account non-gravity,
Yeah, okay.
dark matter couples to psi, whatever that is, Higgs, V, whatever.
Yeah.
Axion lines, whatever. You are now proposing to the literature a new way to flow dark matter.
Good.
Also,
Good.
I don't know what gonna happen, what would happen, but for example, here we just see vectorial interactions. So if you consider like vector axial interactions, it could also be another way to probe it.
I
and
see.
So on.
Uh-huh.
It could, for example, change the temperature of the neutron stars at the end of the day.
What related to my previous question, so I
I
was
see.
why is gravity? What do you mean by link?
Without interaction between the sectors. Yeah, that's right. Yes, this is a very good question. I really don't know papers that do in this way, but maybe can be only ignorance by my part. But I don't really know if there is something in this direction or not. Yeah.
Thank you for the talk. It was really good. And I have a couple of questions. First of all, you consider fermionic dark matter. Is there any kind of study that you consider bosonic dark matter?
Yeah.
Mainly bosonic dark matter.
Bosonic dark matter. Yeah.
Yeah. Instead of the fermionic one.
This one, for instance.
Mm-hmm.
See, of course, here in the pressure, we do not have a degeneracy pressure because we are
Okay.
talking about bosons, but we have a term that comes from the scalar interaction.
Mm-hmm.
So this is essential to construct any kind of compact stars from the dark sector.
Mm-hmm. Okay. And you was consider. My question is, the temperature inside of these stars are really high, kind of billion of Celsius, stuff like that.
No, the temperature, you mean?
Yeah, inside the stars,
Uh,
the neutron stars.
Yeah. Here we are considering cold neutron stars. Actually, we
So
have cold. Yeah, temperature is zero in. Yeah, one MeV in our units. 1 MeV is 10 to the 10 Kelvin.
Okay, but
You
kind
see?
of it's kind of realistic to consider.
Yeah.
Okay.
Yeah. If you have a temperature, we are actually the temperature in stars are. Let me see. In this supernova stage, you can consider temperature different from zero in this stage to see the impact in the later stage. But here in particular, we are considering cold compact stars.
Okay. And you talked about the gravitational wave signatures. What kind of signatures would be?
About
Gravitational wave signatures
the gravitational waves.
would be in binary systems.
Yes, that's right. The recent discovery about the gravitational waves in the case of binary systems. Yes, let me show you. This one, for instance, is signature here, okay? Directly in the mass radius diagram. They can translate all the observational data to this graph. So this is important, so we can discard phenomenological models if we are not compatible with this kind of data. Okay?
Okay, great. Thank you.
Thank you.
Hi.
Yeah.
In slide 10 or 11, I think, you showed us a plot of the pressure increasing and decreasing. And when you study that for liquids, that's actually unstable, and you have to do a Maxwell construction.
Yeah.
Does this also show up in nuclear?
That's right.
Yeah.
Yeah. We see a liquid-gas phase transition in this kind of models that are also presented in finite nuclei. Okay. We can use the Maxwell construction. We see all the first order phase transition, and all of this stuff.
Yeah.
Possible.
And in slide 37, you show the plot for the bosonic and fermionic case, and to me, they're exactly the same. Should it be like that?
Which slide?
37.
This one?
Yeah, they seem the same to me.
Yeah.
Is that expected?
Because of this observation, I put this plot here, because if you see in a particular neutron or quark star mass here, for instance, we see that either the bosonic case or the fermionic case reach the same radius, kind of, okay? So in this case, the dark sector produced by the profile produced by the dark matter here is it's not greater than, because let me show you, how we construct this curve. Because we have two masses and two radii, one for dark matter, one for visible sector, okay? How we construct this one, only one mass and radius. We solve the TOV equation. And if the pressure needs to be 0 in some radius, if this radius in which this guy is 0 is greater than this one, so the radius of that previous diagram will be this one, okay? And the mass will be the corresponding total mass. So in this case, we have for bosonic and fermionic case, practically the same mass, the same radius, okay? But if you consider a dark matter with different mass, for instance, if we decrease the bosonic mass from 15 GeV to 2 GeV, we see that this profile here presents a dark matter halo. So in this case, we would take this radius as the radius that we presented in the previous slide, so the mass radius relationship would be completely different if we consider different values for the dark matter particle. Okay?
Okay, more questions? If not, let's thank Odilon again.
Thank you.